In microbiology, so much of getting the right answer comes down to one thing, starting with the right amount of bacteria. And today, we're going to talk about a surprisingly simple tool that helps us do just that. It's called the McFarland standard. We're going to break down what it is, how it works, and why this basic visual check is so incredibly important in modern medicine. All right, so here's what we've got on tap. First, we'll get a handle on what these things actually are. Then we'll dig into the cool chemistry that makes them tick. After that, we'll see how labs actually use them, from just eyeballing it to using high-tech gadgets. And we'll wrap up by seeing why this all matters so much in the world of automated testing. Okay, so let's get right to it. What is a McFarland standard? Well, the easiest way to think about it is like a ruler for cloudiness. It's basically a set of reference solutions, each one with a very specific known level of turbidity. And we use it to make sure our bacterial sample has just the right density before we start any tests. And trust me, getting this first step right is absolutely crucial for getting those reliable results that doctors and patients are counting on.
All right, let's dive in with the basics. What are we even talking about when we say turbidity?
This is what we're talking about. See this series of tubes? Each one has a specific McFarland value, usually going from 0.5 up to 4.0. And you can see it right away, right? As that number gets bigger, the liquid inside gets cloudier and cloudier. And that card behind them with the bold black lines, that's called a Rickerham card. It's a super simple but clever tool to help us judge that cloudiness. We'll talk more about that in a bit. Okay, but here's where it gets really interesting. That cloudiness you see, it's not actually from bacteria. Nope. It's a clever little bit of chemistry designed to look exactly like a bacterial suspension. So let's peek under the hood and see how it's done. So this table tells the whole story. The cloudiness isn't bacteria, it's created by a chemical reaction. It's all about mixing super precise amounts of two things, 1% barium chloride and 1% sulfuric acid. For that common 0.5 standard, you'd mix a tiny amount, just 0.05 milliliters of the barium chloride with 9.95 milliliters of the sulfuric acid. When they mix, they create this fine white powder, barium sulfate, that stays suspended in the liquid. And that very specific recipe creates a cloudiness that perfectly mimics a certain number of bacteria. And here is the magic number, the key takeaway, that 0.5 McFarland standard, which, by the way, is the one you see used most often for things like antibiotic testing. It's equivalent to a bacterial sample that has about, get this, 150 million cells per milliliter. It's just a simple way to eyeball a massive number of microbes. Now, you could technically mix all these chemicals up yourself in the lab. But let's be real. It's way more common and, frankly, a lot more reliable to just use these pre-made commercial kits. They come perfectly sealed, already certified, and ready to go. This ensures that every test is consistent, whether you're in a lab in New York or a lab in Tokyo. Okay, so we've covered what they are and the chemistry behind them. Now for the fun part. How does a lab tech actually use these things to get a sample ready for testing? The core idea here is incredibly simple. It's basically a matching game. You have your tube with the bacteria in it, and you have your reference McFarland tube. You just hold them up side by side. Is your sample too clear? Add more bacteria. Too cloudy? Add a little more saline. You just tweak it until the cloudiness of your sample is a dead ringer for the standard. And this is that classic method I mentioned earlier, using the Rickerham card. You hold both tubes, your sample and the standard, right in front of those black lines. And you're looking for that sweet spot where the lines behind both tubes look equally blurry or distorted. Once they match, bam, you've hit your target density. And this is just a brilliant example of how simple the principle is. You don't even need an official Rickerham card. Seriously, any background that has some sharp contrast will do the trick. You could use the texture of a paper towel, or like you see here, even just the text from a newspaper. It all works. Now, to get an even better look, a lot of techs will use a light source. By shining a light from behind the tubes, it can really help you see those subtle differences in cloudiness. It just makes it a little easier to nail that perfect match. But let's face it, the human eye isn't perfect. What looks like a match to me might look slightly different to you. So to take all that guesswork and subjectivity out of the equation, a lot of modern labs use digital instruments, like this DensiCheck here. It's a turbidimeter. Basically, it shines a beam of light through the sample and gives you an exact digital number for the McFarland value, no guessing required. Okay, so why? Why do we care so much about getting this cloudiness
just right. I mean, what's the big deal? Well, it's a huge deal, especially when we start talking about automated testing systems.
And this is where it all comes together. These incredibly sophisticated machines, like the Vitek 2 system, are workhorses in the modern microlab. They identify bacteria and figure out which antibiotics will kill them. But here's the catch. All of their calculations, all of their results are completely dependent on starting the test with the exact right amount of bacteria.
And when I say exact, I mean exact. The tolerance is razor thin. For most of the common bacteria, both gram-positives and gram-negatives, look at the requirement for antibiotic susceptibility testing. It's 0.5 McFarland, plus or minus just 0.05. If you're outside that tiny little window, the results could be wrong.
And it's not a one-size-fits-all deal either. Different bugs have different needs. For yeasts, the machine needs a much cloudier sample, somewhere between 1.8 and 2.2 McFarland. And for those tricky anaerobic bacteria, you need a suspension that's way, way denser, all the way up in the 3.0 to 4.0 range, just for the machine to identify them properly. Which brings us to the final and most important question. Thinking about all these different requirements, what happens if you get it wrong? What are the real-world consequences of a sample that's a little too cloudy or not cloudy enough? Well, the consequences can be huge. An incorrect suspension could cause the machine to say an antibiotic is effective when it isn't. Or worse, say a crucial antibiotic won't work when it's actually the patient's best hope. It just goes to show you that this simple, almost century-old technique of just matching cloudiness in a tube, it's still one of the most fundamental and critical steps in the lab, with a direct line to patient outcomes every single day.